Hi guys, so I'm going to go over section 10.1 part 2 with you today again. I apologize, this video is maybe a day late here, but hopefully everything will be okay for you. Any case, so we've done a confidence interval for a difference in proportions. Now I want to do a hypothesis test or a significance test for a difference in proportions. So confidence interval was, let's try and estimate what the difference in proportions would be. Significance test is test the claim that the proportions are the same. So this is really not the same thing as a confidence interval. Confidence interval, we try and estimate plausible values for the difference in proportions. For the hypothesis test, we're trying to test the claim that the proportions are the same. Okay, and this is what it would look like if the proportions are the same. But we actually more commonly write it like this. If I subtract the population proportion 1 from population proportion 2 from population proportion 1, I would get 0, which means they're the same. Okay, we usually use this form in AP statistics, but you should understand both of them. Okay, and so we also want to test if what we see in our sampling is just due to random chance, or does it reflect an actual difference like it says here? Okay, is this something that's really going on in the population, that these two populations have the same proportion, or is it just an accident that just happened by chance? Okay, and we want to assign a probability to that, just like we've been doing with all our hypothesis testing. So remember, we're always testing a claim about population proportions that they're the same. Okay, that this is happening. All right, or this is the way we write it. If you subtract them, you get 0. So please remember, you don't write p hat ever as your hypotheses. It's always, we're testing a claim about population parameters, population proportions. So let's talk about how can I do my test, check conditions. Well, random condition, similar to a confidence interval for a difference in proportions. The data come from 2 independent random samples or 2 groups in a randomized experiment. Okay, so 2 different groups that were randomly created through random assignment in an experiment. And then if I'm sampling, check 10% condition. So 2 things going on. The samples are independent, and the 10% condition is met for each sample. Okay, and then large counts. This is a bit different from a hypothesis test for a single proportion. When we did a hypothesis test for a single proportion, we actually used what we called p sub 0 here. Okay, but now we're not making a claim about one of the proportions. We're just saying that their difference is nothing, that they're the same. So there's no claim for what P2 is. We're not making a claim about P2. We're just saying that P1 minus P2 is 0, or they're the same. So I don't really have a P sub 0 value here, P1 sub 0 or something to use here. So we just use P hat. Okay? So just remember that. That's a little bit different from a hypothesis test for a single proportion. In that case, we use P sub 0. All right? And so that's the conditions that you have to check, or those are the conditions that you have to check. And if this is true, if we assume that that's the truth, that's how hypothesis test works, we assume that the null hypothesis is true, the 2 parameters are the same. And we call their common value P. But what is P? Like what is this? What is P? Okay? So what we do is we come up with some kind of an estimate for P, and we call that P sub C, P hat sub C. All right? And this is called a pooled sample proportion, So what you do is you take the number of successes from the first sample and add them to the number of successes of the second sample, and divide that by the sum of the sample sizes. Just remember, this is not normal fraction addition. So normal fraction addition works this way. when I have 1 over 3 plus 2 over 3, I get 3 over 3. Okay, that's normal fraction addition. That's not what this is saying. This is saying if I have 1 plus 2 over 3 plus 3, this would be 3 out of 6. Okay, so this is what we're talking about here, not normal fraction addition. Just remember that. Right? Any case, so we're going to use p hat sub c, or the pooled sample proportion, to calculate the standard deviation or standard error of our distribution, okay, of our sampling distribution in this case. That's where p hat sub c comes in. I don't want to go too much into detail. Usually students ask me 400 questions about what is p hat sub c, why do we do this, what's going on. There's a lot of reasons, but I want to keep the video short. So if you have a real big issue with that, you can contact me and let me know, okay? And I'll explain it to you further, hopefully, if you have questions about that. So here is a two-sample z-test for p1 minus p2, okay? Suppose the conditions are met, so you check the conditions. Then to test this hypothesis, we first find p hat sub c in both samples combined. Then we compute the test statistic. This would be our do step. Then we find the p-value for my test statistic. Again, if it's a one-sided test, we get doing one-sided probability like this. And if it's a two-sided test, we're getting twice the probability of the corresponding one-sided test. Okay, but your calculator should do all this work for you. You shouldn't have to worry about this too much. Conceptually, you should at least understand what it is we're doing again, just like hypothesis test for one proportion. Okay, so let's do one together, and then we will maybe do a second one, which is an experiment, right? So this one is not an experiment, but the second one I think is an experiment. So it says researchers designed a survey to compare the proportions of children who come to school without eating breakfast in low-income elementary schools. So there's a lot of research about correlation between not eating breakfast and doing poorly in school. This is why people care about this kind of a situation. So it says an SRS of 80 students from school 1 found that 19 had not eaten breakfast. So there's my sample size for the first one, and here's my what we call our X value, our success values. Okay, so X1. At school 2, an SRS of 150, so this is my small n1, this is my small n2, included 26. So this is my number of successes from the second sample who had not had breakfast. More than 1,500 students attend each school. Okay, that's my population size. Do these data give convincing evidence of a difference? Do these data give convincing evidence of a difference? So, is there a difference or not? That's basically the question we're asking. So, do they give convincing evidence of a difference? What this means is my alternative hypothesis is going to be two-sided, because they're not saying do we believe that school 1 has a higher proportion than school 2. Okay? We're just saying, is there a difference? All right. Carry out a significance test at significance level 0.05. All right, so we'll do state, and we'll say we will perform a test of null hypothesis is always P1 minus P2 is 0, or the two proportions of students who eat breakfast at both schools are the same. And then alternative hypothesis is P1 minus P2 is not 0. Okay? Is there a difference? Is there a difference or not? Okay? That's what we're saying. So, again, remember we have to define our P1, P2 if you do stuff like this. So we say where P1 is the true or population proportion of students who did not eat breakfast at school 1. Who did not eat breakfast at school 1. Okay, so school 1. All right. And then P2 is the true or population proportion. Man, I'm messing that up, sorry. Proportion of students who did not eat breakfast at school 2. Okay. So school 2, we got it. Okay. So, and then we will say, let alpha be that. Remember, you state your significance level before you start always. Okay. And then you say plan. And as usual, if conditions are met, we will perform a, and now the name, of course, this is a 2-sample z-test for P1 minus P2. Okay, so this is the name, important 2-sample z-test for P1 minus P2. All right, and then so name the procedure, that's naming the procedure, and then random. Okay, random. It is given that both samples are SRSs. There it says SRS, SRS. Are SRSs from their respective populations. Okay, so that's fine, normal. Again, I'm checking each sampling distribution for normality, and then we're assuming that the difference is also normal because we know that from what we did in chapter 7. Okay, so normal, I'm doing n1 p hat 1 greater or equals to 10, which is, if you do that math, this was 19 successes. Sorry. N1 is actually my sample size, forgive me. N1 is 80, that's my sample size, so 80 times P hat 1 is 19 out of 80, but you know that's always just going to be that number, 19 successes. Okay, and N1 minus P hat 1, which is 80 times, what's that, 61 over 80, and we know that that's greater or equals to 10. All right, and then we check N2 P hat 2 greater or equals to 10, and my sample size 2 is 150 times P hat 2, number of successes, is 26 over 150, but we know that that's the case, that's greater than 10. And N2 times 1 minus P hat 2, and that would be 150 times 124 over 150, and that's just 124 like that. Okay, so you just say the normal condition is met. Annoying. And then independent. All right, independent. So now we have to say that, checking our conditions back up here, the samples are independent, and 10% condition for each sample. Okay, so let's just say it is safe to assume that these samples are independent, since they are random samples from two different schools. Okay, there's no way to feel like somehow there's a systematic influence between students in one sample and students in the other sample. That doesn't seem to make sense since they're randomly selected from two different schools. And then check the 10% condition. But they told us that there's at least 1,500 students at each school. And so we can just say, since there are more than 800 students at school 1 and 1,500 students at school 2, the 10% condition is met. Okay, so I'm not sampling more than 10% of the population. Fine, then go to the do step. All right, now we wrote the proportions there. P hat 1 is 19 over 80. P hat 2 is 26 over 150. Okay, so remember, to do this, we have to calculate P hat sub C, the combined proportion, which is this thing that I scribbled all over right here. Okay, P hat sub C. So we want to calculate this thing. Okay, so the way you do that is to say, okay, that means P hat sub C, the pooled or combined sample proportion, is 19 plus 26 over 80 plus 150. And that gives me 45 out of 230, which is about 0.1957, something like that. Okay? All right. So now we just plug stuff in to our formula. So here's my formula. My test statistic is Z equals P hat 1 minus P hat 2 minus 0. Okay, that's our null hypothesis. We're assuming that they're the same. P1 minus P2 is 0. Over the standard deviation of the combined proportion that we're estimating. So it's this over N1 plus P hat sub C 1 minus P hat sub C over N2. And we get this. Alright, so if you plug stuff in, we get 0.2375 minus 0.1733. Those are those two proportions. Minus 0 over, and then we just plug stuff in here. Okay, so this is P hat sub C, which is 0.1957 times 1 minus that, all over N1 is 80, plus again 0.1957 times 1 minus 0.1957, all over 150. Okay, that's annoying to write. Okay, in any case, you have all that, and then you want to get the answer. Please don't type this in your calculator. Stranger danger. Do not type that in your calculator. Okay, so what you do is just go do the test on your calculator, and down here it's a 2-prop-z test. Okay, so we call the procedure 2-sample-z test, but it's a 2-prop-z test on your calculator. So stat tests, 2-prop-z test. And then you're just entering in number of successes, sample size 1, number of successes for sample 2, and then sample size 2, and doing a test that's two-sided and calculated. Okay, I don't feel like I need to make a video for you how to do this. This is pretty straightforward. And then you get all the information you want. Okay, it's beautiful. So my test statistic is about 1.168. Okay, my test statistic is about 1.168. And then I can write my probability statement. It's a two-sided test. So what's the probability that z is less than or equal to the negative of this test statistic, or z is greater or equal to the positive version of that test statistic? Okay, remember we're talking about this situation. Here is negative 1.168 and here's 1.168. Okay, two-sided test, we're calculating this area right here. All right, and that's the same as saying, now you can write this also like this, union like that, all right, and this is independent, so you can just add the two probabilities. So what you get basically in the end, we already have the answer. Our p-value was given to us here. There it is. The p-value is 0.243 if we round to the thousandth. So 0.243. That's my p-value. All right? And so we conclude and say, since the p-value, which is equals to, I should write p-value. Since the p-value, which is equals to 0.243, is definitely greater than alpha, which is 0.05, we fail to reject the null hypothesis. So if I fail to reject a null hypothesis, I don't have sufficient evidence to conclude that there's a difference in proportions. Okay? We don't have sufficient evidence to conclude that there is a difference in proportion in proportions of students at the two schools who didn't eat breakfast. Okay, so I can't say that there's a difference. That's all, because my sample proportion is probably too close to each other. All right, so that's that. So please go check this out by yourself. There, that you have the calculator situation. There's an 89 and a 84, and then the next one is just another test. I think I should do this with you too. I don't really want to write all this and make your video super long, but I think I should do this with you too. So basically all this part of the note sheet states is that the distribution we get for an experiment is actually not a sampling distribution. In this case, we got a sampling distribution that we checked the normality of right here. We checked the normality of a sampling distribution of the difference in proportions. That's basically what we did there. In this case, it's not sampling distribution if we do an experiment, because in an experiment I'm not selecting from a population, I'm assigning randomly to treatment groups. Okay, so I can't really go into detail here. Your textbook doesn't either. This is really complicated actually. Sampling distribution is much easier to understand than a randomization distribution. This is really complicated. And so I've looked over the years for a good way to explain this to you, but it's really difficult without getting very, very complicated to explain this to you. So let's just look at this and go, oh, the textbook says if I do an experiment and I assign randomly one group of people a treatment and another group of people placebo or control or whatever you want to call it, and I look at those proportions and I subtract them, I still get a distribution that's about normal as long as each individual sampling distribution for p hat and p hat 1 and p hat 2 were also normal. So just realize that sampling distribution and randomization distribution really are not the same thing. This is a very, very big difference. But we're just going to kind of go, oh, okay, it kind of works the same in any case, so let's not think about it too much, because it's really outside the scope of this course, okay? So, any case, let's leave it at that. Smile and be happy, because the normal condition that I check works the same as for a sampling distribution. Randomization distribution and sampling distribution, for us, we treat them the same for the normal condition, and therefore all the statistics just work the same. Life is good. Okay? So let's leave it at that, and let's do an experiment together, and then we'll be done with section 10.1 part 2. Okay, so example 2 says, high levels of cholesterol in the blood are associated with higher risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? The Helsinki Heart Study recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate this question. The volunteer subjects were assigned at random to one of two treatments. Okay, so many men took the drug gemfibrozil to reduce their cholesterol levels, and a control group of 2,030 men took placebo. Okay? So treatment versus placebo or control. During the next 5 years, 56 men in the gemfibrozil group and 84 men in the placebo group had heart attacks. Is this apparent benefit of gemfibrozil statistically significant? In other words, is this number sufficiently low compared to this number that I can say it didn't just happen by accident? That's the question. Okay, is the 56 out of 2051 so much less than the 84 out of 2030 that I can say that difference is not just an accident? There must be an influence by the drug. The drug must be making the difference. Okay, it's not just by chance. It's statistically significant. There's a very small chance that this just happens randomly. Okay, that's what we want to check. So we do a test. So this is different. Is the apparent benefit of gemfibrozil statistically significant? This suggests is the population proportion of men who take the drug actually less than the population proportion of men who don't take the drug. So this suggests an alternative hypothesis that is one-sided, saying that is the population proportion for these guys actually less than this population proportion? Okay, so that's my alternative hypothesis. That's what we're saying. All right, so let's do this. This says same business state. We will conduct or perform a test of, and then write our hypotheses. The null hypothesis, always the proportion of people who got a heart attack for both groups are the same. And then the alternative hypothesis is that the proportion of people in group 1 who got a heart attack is actually less than the proportion of people in group 2. Okay? Now it's very, very important, since I'm making this claim, that I define P1 correctly and P2 correctly. Okay? So we have to say, and this is weird. I have to admit, the way you define this is kind of tricky for an experiment. It's a little bit different. So please pay close attention to this one. We say where P1 is the true proportion of middle-aged men like the ones in this study. So, like middle-aged men, comma, like the ones in this study, comma, who took gemfibrozil and had a heart attack. And P2 is the true proportion of middle-aged men, like the ones in this study, who took placebo and had a heart attack. A placebo, I guess. And had a heart attack. This is annoying, okay? This is quite different actually, because remember, we're not sampling from a population, so I can't do inference back to my population. But we're saying, hey, I can do inference a little bit wider in scope than just my treatment group. And the way I can do that is by saying people who are like the people in this study. Okay, so it's fair to assume that if you're like someone in this study who got this treatment, that you will respond the same way. Okay, so we're saying this is useful for people besides just the actual participants in the study. Otherwise, what's the point of doing experimentation? Okay, so that's tricky. All right, so be careful with that. All right, so that's the state part. Plan. Oh, and then we have to say, actually what I did, and I think this is not necessary, but what I did is say let alpha be 0.01. Since this is a medication to lower your risk of heart attack, maybe we should have a stringent bar. Okay, so we make alpha 0.01. So we're very sure it's not just an accident that this happened. Okay? Alright, so then plan if conditions are met, we will do a 2-sample z-test for P1 minus P2. Okay? And then we do random. Okay? Now, this is different. You don't say random sampling. You say the volunteers. Pretty sure it's what it said. The volunteers were assigned at random. Okay? So you say the volunteers were randomly assigned to groups. Okay, that's my random condition. And then normal, and we check the normal condition again, n1 p hat 1 and n1 1 minus p hat 1 must be greater or equals to 10. Alright, and then we just do it. So we say 2051 times 56 over 2051 greater or equals to 10, which is 56 greater or equals to 10. And I realize that this seems kind of ridiculous, but you're showing your work very clearly. So 1995 over 2051, and that's definitely greater or equal to 10. Okay, so that's for sample 1, and then for sample 2, check this distribution shape, and this is p hat 2, and this one, and 2, 1 minus p hat 2. Okay, so large counts condition here, and we do the same thing. We get 2030 times 84 out of 2030. And this would be 2030 times 1946 over 2030, which seems ridiculous to be writing all this. Okay, so I get that and this. Okay, so definitely the large counts condition is met, so you can just say the normal condition is met. All right, so remember, this is a randomization distribution, but because each distribution of each sample distribution here, or each distribution of the group of people who were randomly assigned to the treatment, I should say, not sample proportion, is about approximately normal, then the randomization distribution will be normal. This is, again, tricky, but okay, let's move on. And then independence. This is also different. It's an experiment, so I can't check 10% condition. So I'm checking two things. Remember, if I can do this, maybe I'll do this. Remember, we had volunteers, okay, and then we did this random assignment to treatment groups, all right, and then there's gemfibrozil here, and there's placebo here. And what we want to say is that individuals inside the group are independent of each other, and the groups are independent of each other. All right? So we just say due to random assignment, it's safe to assume that the groups are independent. Okay. All right. And when we say the groups are independent, we mean their responses to placebo or gemfibrozil are independent. And then we say that the individuals in each group should also be independent. Since one individual's response or to treatment or lack thereof is independent of another, okay? Since, let's say, one individual's what should we say? Individual's heart attack response is independent of another. Okay, yeah. So there we go. We've checked the conditions: random, normal, independent, and now I want to do the do step. Okay, do step. Back to the same thing again. P hat 1 is 56 over 2051, which is 0.0273. P hat 2 was 84 over 2030, which is about 0.0414. Those are pretty close to each other. And then my combined proportion, my pooled sampling, well, my pooled randomization proportion, I guess is what we should call it here, is 56 plus 84 over 2051 plus 2030. and that is 140 over 4081. And that would be 0.0343. Okay? And so we have all that information. We can do my test statistic again. Test statistic is this, p hat 1 minus p hat 2, minus the assumption that they're the same, over p hat c, 1 minus p hat c, over n1, plus p hat c, 1 minus p hat c, over n2. Okay, plug in the numbers, and they may draw a long line there. 0.0273 minus 0.0414 minus 0. Please be careful. Making a small error here makes a huge difference in your answer. Okay, so that's unfortunate, but if you like transpose two numbers or something, you're in trouble. 343. That's what we got for p hat sub c, and then 0.9657 over n1 was 2051, plus same thing again, 0.0343 times 0.9657 all over 2030. Okay, again, do not enter all of that in your calculator. That's disaster waiting to happen. If you do it in a round, I think you get this approximately. Okay, and then we're doing this. What is the probability that z is less than, because my alternative hypothesis was less than, so z is less than negative 2.47, and that p-value I think that you get is 0.0068. Okay, so then I write my conclude statement, and the conclude statement is, since, that's a very low p-value, since the p-value, which is 0.0068, is less than alpha, which is 0.01, we reject the null hypothesis. There is convincing evidence that the proportion of middle-aged men like the ones in this study who took gemfibrozil and had a heart attack is lower than those who took a placebo, than those, I'll just say than those who took placebo or take placebo. Okay, so gemfibrozil is effective, basically, is what we just said. All right, hopefully that's clear for you guys. Another fairly long video. Have a nice day.